Sir, you are muted.
Can you hear me now? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Ah, fine. Happy New Year.
Same to you,
Happy New Year, sir.
Happy New Year, sir.
Wait a minute. Now I will start. कहाँ से आ गया ये सब? तुम्हारे पास वो नोट है टोपोलॉजी बेसिक्स? Because I will start with the review of that. I think you should have that. Okay, let me start. Hello, can you hear me?
Yes, sir.
So topology, remember, first we should remember the metric space. Okay, fine.
Yes.
Oh. You should remember the metric space. So that first have the review of that. Basically, a short revision. Basically, we are going to this course in topology. So basically, X you have a non-empty set. Previous note 16 and topology. This topology means basically you have this is a subset of the power set of X satisfying which satisfies conditions. One, both X and phi empty set belongs to tau. Two, if this is any family, arbitrary family, Y, I belongs to I. This index set I may be finite, may be infinite. If then its union. Also belongs to tau. That means arbitrary union of the members of tau. Arbitrary, anything it can be. Union of the members of tau is again in tau. Okay, right. The first one, 2 and 3. Finite intersection of members. I have taken 2, but by induction it will be same thing. So finite intersection of members of tau is again in tau. So here you should be careful. For intersection, it is only finite. That you should be careful. Okay. So we have a non-empty set X, and there you have a collection of subsets of X satisfying this. The X belongs to tau, phi belongs to tau, and arbitrary union of members of tau belongs to tau and finite intersection. Okay. If you have this, then tau is called a topology first. Is called a topology. On X. And the members of tau are called open sets. More precisely, because on a set X you can have different topologies. So if you sometimes, if you're considering more than one topology on the same set X, then it should be clear that we are considering open sets with respect to which topology. In that case, we will say that it is tau open sets. That means they are open with respect to the topology tau open sets. Okay. Now, look, I have given examples again. I am going to consider that. Okay. So these things I explained in page 125 previously. Okay. So these are open sets. Okay. The closed sets is the, it's just complement. The definition 3.3, I put that. So you have a topological space. And another definition, A subset of X you take, then A is called closed in X, or means X tau more precisely, because closed is defined in terms of the tau. If X minus A is in tau. Okay, so since it is through coming complement, so if we apply De Morgan's law, okay, in this case you will get 1, X and phi are closed sets. Okay, but true. Here, since I'm taking complement, so it will be, look, what will come? Arbitrary. I told you last time that if you have between open and closed sets, you think there is a relation like this: union, intersection, open, closed. Okay. So arbitrary union of open sets is this. So union, you are changing this intersection. There also you'll have to change open sets by closed sets. Arbitrary intersections of closed sets is closed. You have replaced open by closed, union by intersection. And the third, purely open sets, finite, there is intersection, union of closed sets is closed. Okay, so this much you get. Now I am giving some examples of topology. Okay, topology, first you see that examples. Examples. Look, by definition of topology, X and phi will always will have to be in a topology. So if you take just tau equal to this, it will give you a topology. Actually, this is the smallest topology in that. That I will tell you what do we mean by smallest topology. So this is called indiscrete. Later on we will define discrete topology. So it's the opposite of that, indiscrete or trivial topology. Trivial topology. It is smallest in the sense if sigma is any topology on X, then tau is actually contained in sigma. Look, it makes sense because they are actually subsets of power set of X. So it makes sense that in that inclusion, tau will be contained in sigma. On the other hand, if you take this, so this is actually the smallest topology because it will be contained in any other topology on X. Smallest topology on X. On the other hand, if we take this, sigma equal to the whole thing, power set of X. Okay. Don't write sigma, take tau here. Tau. Okay. If you take tau equal to this, then it is a topology. Trivially, nothing to prove actually. Then any topology, if like sigma is any topology this here, then sigma will be contained in tau. This tau is just notation. Here tau is the trivial topology. Here tau is the whole thing. This is called the discrete topology. That means here open sets are, everybody is an open set. Every subset of X is open, whereas only two open sets are there, X and 5. Discrete. So it is called the largest topology. The largest topology on X. So two topologies. So that means, but I told you last semester, again I am telling you, this is very small, this is very large. Okay. So for our fruitful study, they are not suitable. Okay. Though often they work as nice counter examples. Say topology should be the good size, should be in between that. That means it should not be too large, too small. It should not be too large. The topology, preferable topology should not be too large or too small. That should be the thing, goal. Okay. You will gradually understand why it should not be. Because particularly topology related to functions and that, continuous functions. So our choice should be a topology, our choice for topology should be such a way that not all the functions should be continuous. On the other hand, reasonably nice function should be continuous. That will give you some control over the topology, automatic. That topology should not be too large, too small. Okay. So that you should keep in mind that if you want to study a good topology, it should not be too large, too small. Should not be too large, too small. So two topologies, first you should remember discrete topology and indiscrete topology. Okay, now last semester you did metric space. Look, it's a metric space. And here you generated open sets. It came generated by interior points. That topology generated by, that is a topology, and we call it tau d. That is topology generated by t, tau d. Okay, so any metric space gives a topology, tau. So any metric space is a topological space. Is it? But a topological space need not be a metric space. I am giving an example that. Okay, tau d. In metric space, we have proved this result. In metric space. In a metric space, xt, every singleton is closed in X. Activate windows. I see. Closed in X. That is X is closed in X tau, more precisely, XT. That will give you the topology for all X belongs to X. Now you see that if you take X, suppose X has more than 1 point. Look here, I have given that example. More than 1 point, this is thing. Now, if you take discrete, indiscrete topology, trivial topology, here open sets are this, so its complement will be the closed sets of these. So these are closed sets. Look, since I have taken more than 1 point, so that means no point is closed here. Closed in X tau. But in a metric space, every point should be closed. That means this topology, trivial topology, can never be generated by a metric D. That means it can never be induced by a metric. That means if what you have got observation, if X has, this is because if X has only 1 point, then obviously it will be closed. More than 1 point, then the trivial topology on S can never come from a metric. You will give later on many more examples. That means here first you get an example. You have a topological space. You have a topological space which is not a metric space. Which is not a matrix. But you may argue that way you will be right that it's not a good topology, it's trivial topology. That's why eventually we will study reasonably nice topology. So look here, first it failed because of not a singletons are closed. So we put a condition so that first condition we should have that singletons should be closed. That means there we put an axiom. These are called the separation axiom, the first thing. So X tau, a topological space, is the definition that I've given. X tau is called a T1 space. T1. There are other axioms, separation T2, T3, T4. T1 space if every singleton in X is closed. Look, actually we should write more precisely closed in X tau, because closed means its complement is open, that is in tau. But often if we do not have any confusion over tau, we just write closed in X. That is acceptable. Okay, so that first example to get every metric space is a T1 space. But you should have, so first thing, this is the first separation actually, T1 space, every metric space. But there are metric spaces, but find a T1 space which is not the metric space. Remember, in this paper you have, if X is infinite, tau, cofinite topology. Have the reason. Remember, cofinite topology, tau is this thing. You have X, phi, A. First, take rather this way, you write X phi union A such that X minus A, cofinite, this means complement of finite. X minus A is finite. These are the open sets. Okay. Tau. You can easily check it's a topology. That is called cofinite topology. Why I am taking finite? Because if you take finite, it will give you the discrete topology. That will be metrism. That will come from the distinct metric. So that will be a metric space. So if you take infinite cofinite topology, then it is not discrete. Then you can check that because of this. Here the closed sets are what? Closed sets, look. Here closed sets are X, phi, and finite subsets. Of X. So particularly singletons are closed. So this is an example. If you infinite, make sure that you take infinite. Okay, if on an infinite set, if you take cofinite topology, this is a T1 space, but not a metric space. We'll see why it is not a metric space. That you should be able to justify. Okay, why it's not a metric space? Okay, well, let us see that why it's not a metric space. Reason is, okay, now T2 space, or how does Hausdorff space? Let me define T2 space, or actually axiomatic founder of topology is Hausdorff, or Hausdorff space. What? X tau is called Hausdorff if given any pair of distinct points xy in X, there exist open sets. This will depend on X and Y. U and V, they are disjoint. U and V such that open sets means open sets in, of course, in X tau, such that X belongs to U, Y belongs to V, and that means distinct ones can be separated by disjoint open sets. Okay, this is called Hausdorff. Any metric space is Hausdorff. This is T2. Look, if you have the metric space Xt, if you have X not equal to Y, then if you choose R, this, you can choose that. You can take dxi by 2. Okay. Look, x since x not equal to y, dxi is strictly greater than 0. Actually, r less than it will work, but I'm just taking 2. Then you can check that B xr, any open ball in a metric space is an open set. Intersection, this is empty. So any metric space is house drop. On the other hand, any cofinite topology, if you take infinite set, any two non-empty open sets must intersect. So here you got metric space is house drop. Whereas you see that if you take this infinite and this is cofinite topology. Now look, if you take two open sets here, you non-empty open sets. Now look, X minus U intersection V will be X minus U union X minus V. Now look, since U V belongs to tau, this will be X finite. Of course, if you take U in X, then it will be empty set. This is also finite. So if you assume this is disjoint, look, if you assume this is disjoint, then this will be equal to X. That means, but X is infinite. Here you are getting union of two finite sets, so it will be finite. So you will get a contradiction. So that means in here you are getting, this is important, infinite, because I told you if it is finite, it will be only discrete space. So it will be generated by discrete metric. So if you take infinite, on that if you take cofinite topology, then any two non-empty open sets must intersect. Any two, what I am getting in general result, any two non-empty open sets must intersect. That means you are not getting any two disjoint open non-empty set, so that it cannot be T2. So this is not T2, but T1. In fact, often in the interviews, both for PhD level as well as faculty interview, often people keep asking questions on that. Give an example of a T1 space which is not T2. So here you will get a space T1 space which is not T2. Okay, but every metric space will have to T2. So that cofinite topology is not, you are proving it is not T2. Okay, so that so this is, so here you are getting a T1 space need not be a metric space. A T1 space need not be a metric space. Make sure of that. Okay. Actual metric space basically has all the nice properties of a topological space. Okay. So that, but your topology comes from a metric, then you have, that means you have a lot of advantage. Okay. That's why we call it define metrizable topology. Definition 3.4, metrizable topology. So that means if you have X tau, if there exists a metric D, if there exists a metric D on X such that, don't confuse, tau is same as, tau is a general notation here. It means the topology is generated by D, and this is the topology, this one. This means the topology generated by this. If there is, then tau is called a metrizable topology. Okay, this thing. In case you have further thing, it is a complete metric. Suppose you have a complete metric. It is quite possible that your metric is complete. Suppose you have it, then we say that tau is completely metrizable. There may be topology which is metrizable but not completely metrizable. Completely metrizable. Okay. Tau is completely metrizable. So that should be the point. And then, okay. So in discrete topology, I have done this everything. For example, 5 examples. For all these examples, you should read. Okay. In fact, that I told you, the comparable topology. Here, suppose you have a same set. You are not changing the set, non-empty set. And suppose you have two topologies on that. Okay. Two topologies. Now, if you have this, then turn, you see that we call sigma is stronger than tau, or we say that tau is weaker than. Look, this need not be true. That I should give example that this need not be true. Is weaker than. That my example 6 will tell you. Weaker than sigma. Okay. Now, this is the definition. Stronger topology, weaker topology. But suppose you have this. That means tau is a subset of sigma, but a proper subset. If tau is a proper subset, then we say that tau is strictly weaker. I am just explaining the term, strictly weaker than. Next semester we'll be doing functionality. There also you'll have something, norm topology. Who is strictly weaker, stronger, that will come weaker than this. Or we say that sigma is strictly stronger than tau. So this way, discrete topology is the strongest topology on a set X. And in discrete topology, trivial topology is the smallest topology, weakest topology, weakest topology. So trivial topology, weakest topology. Discrete topology the strongest topology. But two topologies may not be comparable. The example 6, look, I have given this, okay? I have asked a question, is it comparable to topologies? On R, I have given this, that you can have this topology on any set, actually, this kind of topology. So R, phi, it is set of irrationals and its complement. This will give you a topology. This is not comparable to the usual topology, because the usual topology, neither of this is open. Okay. On the other hand, in usual topology, you have this is closed open interval 0, 1. This is open. That is not open here. This tau is not. Hello? क्या problem है? Tau is not comparable to the usual topology usual topology on R. Okay, usual topology on R. In fact, this example you can have something like this topology. What is going on? That is not. Wait a minute. Oh. Okay. So that this is not working. So that suppose you take X, any non-empty set, of course, and you take a subset of X. Then if you give this X, phi, A, X minus A. This will be a topology. Is a topology on X. Look, A need not be non-empty. If A is empty, then you will get only X and phi. If A is empty or A equal to X, then actually you will get this will be a simply X phi, trivial topology. समझ गया? Okay. So this you can tell. That means if you want to avoid non-trivial trivial topology, it has to be actually a proper non-empty subset. But in that case, you need X should have more than 1 point. If X has more than 1 point, because if you have only more than 1 point, then you can have a non-empty proper subset. And A is a non-empty proper subset of X, then this topology X phi A is a non-trivial topology. Okay. Well, fine. So look, first that means you have defined topology. You have defined T1 space, T2 space, T2, which is also called Hausdorff space. Felix Hausdorff. This is in English, we have seen that it is equivalent to that, Phillips. Okay, Felix Hausdorff. So that now this is the main thing. So this is, we got the topology on that. Now, next thing you should have the neighborhood of a point. That already I told you, explained last semester. You can again read here. So since we do not have a concept of the distance here, so what we'll do, suppose you are taking a topology called space and X belongs to X. Then suppose U is an open set. That means U belongs to tau such that X belongs to U. That means any open set U containing X. Then U is called a neighborhood of X. In short, we write N-hood. Neighborhood of X. More precisely, you should write this. Since any open set, so that actually this open set will be a neighborhood of for each of its points. Okay. because since it is open. Okay. Now the thing is, let me explain that some people here, I am just giving a caution. If you're reading from some topology book and if you find something definition neighborhood, some people take, let me tell you, some authors take definition of neighborhoods like this. They not necessarily take open set. Suppose W, the subset of this, and X belongs to W, then W is called neighborhood of X. W, I am not assuming open. In X tau, if there exists an open set U in X tau such that you have this. No. Still I have the open set, that condition is required. Then W is also called a neighborhood. So here in this definition, the collection of neighborhoods of X will be pretty large. Okay, because it is coming through open sets. And here the authors, if U itself by definition is an open neighborhood of X, and the U is called an open neighborhood. In that case, they make a distinction, open neighborhood of X. U is called an open neighborhood of X. Here you will get in some books. Okay, but actually you do not get any advantage out of this. Okay, except in very advanced topology and that we do not get advantage. In fact, analysts, they prefer definition of neighborhood which I gave, open neighborhoods. It is a question of that analysts, they prefer this definition. They always take basically the open neighborhood. Whereas topology is for generalization, they take this thing. Okay, so I will take the neighborhood always open neighborhood. Okay, in next semester also in analysis or what function analysis, what you do, they usually will get by neighborhood, they mean open neighborhood. Okay, so be careful that that my neighborhood is always open neighborhood. The definition 3.5, definition 3.5. Okay, right. Now, look, I have started with topology. I have not started with interior point, closure point. So that now I am going to define interior point, closure point. Interior point, closure point, and boundary point. These points you should understand. And here is a special point, accumulation point. If you want to understand topology, all these points you'll have to understand. Accumulation point. Look, interior point, basically by language, it means it should be inside the interior of this. So that if you take X tau is a topological space you are starting. In metric space, we came from the other direction. We defined interior point, then we defined open sets. And here topology we are starting point is open sets. So that we are coming from that open set. Suppose X belongs to A is a subset of X. Okay, right? Then X is called an interior point of X if there exists open set U in X, that means X tau, such that look, by the definition of neighborhood, that means A contains the neighborhood of X, that is A contains look here, why interior point on that? This is neighborhood open. Because when you do actual analysis on that, boundary points, it will be that will always make problem for your definition of functions, everything. But in the open set, it's not that much problem. That's why we take this interior point. Okay, so that is called interior point if A contains a neighborhood of X, and int A notation means interior of A, or some people use this notation, is the set of all interior points of A. All interior points in A, of A actually. Set of all interior points of. First you are defining interior point in a set, and then you are defining the interior of A. Okay, so interior element means it really is inside that set X. Okay, later on you'll see that when I say X belongs to A, rather X belongs to interior of A, that means it is deep inside A. It is not like something boundary of A. Okay, so basically it means it is away from complement. When X belongs to A, interior A, it means it is away from X minus C, the complement. That's the idea. Okay, here exercise 1 I have given. Be careful. Actually, I should have told you that. Exercise 1 and 2. Actually, exercise 2 should be branded 1, this should be 2, because in order to do exercise 1, you will need exercise 2. So that first you do exercise 2, then you do exercise 1. Okay, right? Got it? Okay, so that interior point, the int. Okay, now I have defined closure point, accumulation point, that I told you last time, like what is the metric space it will have, because we are picking up the definition, the idea from the metric space. So in the definition 3.7, you should have closure point, accumulation point, boundary point. Okay, the closure point, you know that what will happen now. Suppose you have a topological space, A is a subset of X. X need not belong to A. X is X this. Then X is called a closure point of A if every neighborhood, every neighborhood of X intersects A. That is, here I am writing. That is, look here, I'm going from here to this. That is, U intersection A not equal to phi for every neighborhood U of X. This is the thing. Every neighborhood of X must intersect. If you take topology to definition, that will also stay same thing fine. Okay. But we will take always open neighborhood. So this is called the closure point. Okay. And A bar is the set of all closure points of A. Some people write it closure of A. If you want to specify the space, sometimes you write this. That means closure of A in X. This is called the set of all closure points. So that there is, you can easily check A equal to A is contained in A bar. A is this. Okay. So this is exercise. First, you should prove that. 1, this is follows from the definition. 2, you should prove A bar is a closed set. Whether A is closed or not, A bar is a closed set. Look, interior was the smallest open set. Look, A intake. Previously we did the smallest. Sorry. The largest open set content in A. When you go for the change on this, the largest, it should be smallest in English language in that, and content should be changed in by the containing. When it, so A is in, if you go for A bar, this is a closed set, you can prove that. Not only that, it will be that this, look what, A bar is largest, smallest, is the smallest. Open should be replaced by closed. Closed set contained, containing. So you should first prove this, and then you should prove this. I think I have given exercise somewhere. Yes. That is the theorem 3.2. Okay. A bar is a closed set. If B is a closed set containing A, then A bar containing. That is the same thing. This is the smallest closed set. Okay. In theorem 3.2, this is part A and this is part B. Okay. Right. So that this will be able to prove this. And so that it will be this, A is closed if and only if A bar equal to A, because this is smallest. Okay. Now here, so this is takes care of all this care of the closest points in that. Now here theorem 3.2. I think last time I told you the correction on that. Part C. That I have not explained either. The set of accumulation points. This is the set of the accumulation points of A in X. Look, a prime is a closed set. I put a star here. You should see that this A prime is a closed set. You need that closed set X star. If you record, if X star is a T1 space, this you need. So your job is to check that if it is not T1, you should find a counter example. Find a counter example. If X tau is not T1, then A prime is not closed. So I say that need X to be T1. Okay, right. Well, the last thing, let me tell you that A prime, that the definition I've given, that a set of all accumulation points. Accumulation points mean what? That it is a special kind of closure point. The strong type accumulation point. Strong type of closure point. Look here, when I say X tau is a topological space, A is a subset of X, X belongs to X, then X is a definition. X is an accumulation point of A if this thing, look, U minus X intersection A not equal to phi for every neighborhood U of X. That means it will intersect in points other than X. Every neighborhood of X, every neighborhood U of X in X tau. This is the thing. This can be written as the same thing. U intersection that I explained us. Because whatever intersection you take, it should not have X in that intersection. This is called accumulation point. And here I am saying that A prime is closed provided you have this thing, the T1. If it is not T1, then why it may fail? That you should think about that. So first you should think of a good space which is not T1. Look, in discrete topology is not T1. Okay. But then if you take a subset of X, you can take a finite that X is infinite, A is finite. Subset of that. Because it's not T1, then what will be the A prime? Okay, that you can think of that. Okay. So this is your homework. Okay, right. So I will meet you tomorrow again, this time 12 o'clock to 11:55 brother. Okay, tomorrow I will send you a invitation then. Okay, okay, see you tomorrow.
Thank you, sir.
Okay, make sure that you read this note carefully again. Okay, if you do not understand this note, if you have problem with this note, you will have problem with the whole course. Okay, so it's very important you do it. Okay, thank you. Bye.
Thank you, sir. Thank you.